Okay, we're finally at the point at which we want to implement the Chebychev transform, and again, all of this code is available on the GitHub, and so you'll see what we're going to do is build this differentiation matrix D for the Chebychev, which takes a derivative. What it also gives back to you is the grid that you're going to be working with. So those are the two important key factors that are coming back from the Chebychev transform that we're building here. So the idea here is we're going to code this up, and so we're going to first of all show how well Chebychev differentiates. Okay? So we're going to take two functions, hyperbolic secant and tangent, because I actually know explicitly what the derivatives are, and we're going to differentiate these. And here is the code. This is the Cheb function and how it's defined. What comes out of this function is both the grid. In other words, we're going to, again, remember, put this on we're going to transform from x to cosine theta, and then we're going to define all the polynomials on that grid. So we get back the domain vector and also the differentiation matrix that's going to come out of this. So this is Cheb is the main function we're going to do. In the last lecture, I showed you what the polynomials look like inside of this grid, inside of this differentiation matrix. And so this is basically constructing all of it here in what we're doing. And then the functions we're going to differentiate are going to be down here, and so here's how we're going to differentiate it. So we're going to define a number of points on the domain. Here it is, 20. And what you do with Cheb is all you do is give it the number of points you're going to discretize. Remember, Cheb thinks you're on a domain -1 to 1. You can always rescale afterwards, but this is very much like the FFT. FFT believes on your domain 0 to 2 pi. This believes you're on the domain -1 to 1, and so what it's going to send back to you is D, the differentiation matrix, and X here, let's call this X2, which is the collocation points on the grid, okay? If you want to take a second derivative, that's D2. D2 is a second derivative, which is just the dot product of D with itself. So in other words, D squared. That's two derivatives. And so what now we're going to do is going to take one function here, some exponent times sine and a hyperbolic secant. We're going to take the first derivative, so just take this dot product, that D matrix with the vector, or a second derivative, take D2 times, so that's it. First derivative, second derivative of these two functions. That's how easy it is. You define, and notice I'm not even defining my domain. I'm letting Cheb do that for me because it's creating these unevenly spaced points. So let's ask how it did. Here's how it did. So what we're looking at here is the original functions, the derivative, and the second derivative. And the solid line there is the analytic solution, and the dots are the approximations. Notice a couple things here. Notice there are no boundary conditions imposed. Okay? This is really important. Remember, for spectral methods, part of what we were trying to do is get away from the restrictions of these boundary conditions. And in this case here, they're not periodic, they're not no flux, they're not pinned, and Cheb has no problem with it at all, right, of differentiating these things. So this Chebychev polynomials become really powerful representations of this. The second thing to notice is the clustering of the data at the edges of the domain, right? So if you can look here, remember this is an unevenly spaced domain. There's a bigger dx in the middle of the domain than at the edges, okay? And that comes with using essentially this x equals cosine theta mapping, right, between points. So that's how you take derivatives, and now we're going to use this derivatives to actually solve a PDE. So we're going to solve the 2D heat equation. So what we're going to do is we're going to take 40 points, we're going to find x and d through Cheb function, just throw it in there, so now it's the differentiation matrix, and here's where I impose my boundary conditions. When I get this differentiation matrix out, what I'm going down here is going to the nth row and the first row, or right, the last row, first row, and putting zeros there. And that is the imposition of no flux boundary conditions. And so there you go. So when I do this, and now I take a second derivative of this to get the Laplacian. And I'm going to say y equals x because now we're going to make it two-dimensional in a second. So what I've done here is I'm creating a second derivative matrix in x, and I'm going to mesh grid this in a moment, to make ut equals uxx plus uyy. Okay? And the way I do this is I can actually make this Laplacian by using the cron command, which we've also done before for building the 2D matrices for finite differences, which is you cron an identity against D2 plus cron D2 plus identity. So what this is 2 derivatives in y, 2 derivatives in x. So this L is the Laplacian in this Chebychev representation. So that's kind of, in some sense, how easy it is to make this Laplacian. And by the way, embedded with these boundary conditions. So I have the boundary conditions embedded, and here's how I have this now represented here as the operator L automatically has the boundary conditions embedded in it. So let's go solve the heat equation. It's pretty easy to do. Let's start here, actually. My solution is I call a ODE solver, because we turn the PD into ODEs. I call the right-hand side, which is right here. We'll talk about it. I send in my initial condition, my time span, and whatever arguments I have. In fact, I'm going to send in my operator L that I just produced, which is the Laplacian. And I send it into here, and all I've got to do with the heat equation is ut equals uxx plus uyy. There it is. The right-hand side is that Laplacian hitting this takes 2 derivatives of the function itself, and I'm done. So there's the 2D heat equation solved using the Chebychev polynomials in 2 dimensions, where I've mesh gridded everything up, and here's what the solution looks like. This is the initial condition, which is a Gaussian. It's diffusing away here over time points. Okay, so just wanted to give you one solution technique for the Chebychev polynomials. I would recommend also, there's a lot more detail about this in Nick Trefethen's book on spectral methods. He has many chapters on Chebychev, and he's also developed a whole package called ChebFun, which really digs down on this. But really, all of this is capitalized on the power of what spectral representation can do for you, right? Which is very accurate, handles much more generic boundary conditions, and it connects to the n log n speed of the cosine transform. So that is this implementation here of a second spectral method. So now we have the FFT spectral, some Chebychev, all that's available to you to solve these problems.